All right, everyone, we are going to continue. Now, before we do so, I will give you some the guidelines regarding the assignment, so how to submit and this and that. We already talked about that. Now, first rule is this. Okay, so either you send me an email or you basically send me a message on Telegram. Please post a PDF file only and nothing else. So I don't accept JPEGs, I don't accept anything else. Okay, so please keep that in mind. So even if you take photographs of something, you make your notes and then you take a picture, please make sure that I will get a PDF file and not an image file. All right, so that's number one. Number two, all right, so I mentioned before, PDFs only. I don't accept anything else, okay, that has security reasons, especially not image files, okay. Basically, the image files can be damaged, so I'm not supposed to take them. So if you send me an email file, send me an image file, sorry, then I will basically ask you to submit it again. Do not resubmit your results. So once it's submitted, then it's submitted, because it makes me it makes it very hard to edit it. So that's the reason. Okay, so please make sure. You need to submit during the time frame that I give you, of course. Okay, so that's not the rule, but that's something is also important, and don't submit it twice. Okay, so if it's submitted, then it's submitted, so take it as is. If you submit handwritten notes, I would like you to ask not to have handwritten notes. I'll give you information about editors. So I recommend LaTeX because that is free, okay, but you can use any other software you like to. I will also give you information about how to use the formula editor in Word, okay. Microsoft is charging you now for that, but I found a way to bypass that. So, but I'm not supposed to say this, but again, I will keep you informed then. So if you basically use handwritten notes, okay, please use either a blue or a black felt tip pens, Filzstift, okay, so that's a German word if you don't know what it is. And it needs to be thick, okay, so because I need to read it, all right? So I don't use basically anything on a sheet, okay, so use blank sheets only, nothing else. And basically I will give you information about editors. So if you don't know how to edit, documents regarding formulas and all that stuff, so formula editors, I will give you information about that, okay? But until then, you can use handwritten notes, but in case you can, please do not, okay? Because it's very hard to read for me, and if it's written by, if you write it yourself, please use a felt tip pen. All right, next, all right, so then I need the following information from you, and the one is basically, that's important, okay? The number of assignment that you submit, so I know basically what you're doing. Your full name, but only for the first assignment, okay? So if you submit your first assignment, you need to give me your full name. But for the second, third, and so on, it's not longer the case. Your student number also. So then I basically, I have the list of your names and I have the list of your student number, but these two lists are not attached, which is completely insane. Okay, so the examination office gives me basically the advice that due to security reasons, the list of your full names and your student ID is not attached to each other, which, to be honest, I don't understand. So, but anyway, okay, so that's that, okay? Now, again, so your student number is needed only in your first submission, and then you need to have a personal identifier, which is, I talked about it, is a kind of a nickname, a fantasy name, a pseudonym, stuff like that, so you can give it to yourself, okay? And you must do that because I'll need to publish your results between, if you don't provide me with that, then I will not be able to publish your partial results, so you only get the full grade by the examination office. I'm not supposed to, okay? Because I don't want to have anything attached to your personal name, whatever, which I upload in the internet. That's not supposed to happen, all right? So the personal identifier can be anything, okay, except a few things that basically I want to mention before. So it must not contain your name. Okay, it's not even parts of it, because it reveals your identity. So anything that reveals your identity is basically not allowed in this case. Okay, so I don't accept it. I will basically ask you to submit something else. It's not supposed to contain anything basically related to your name and your initials, of course. And it's not your student number either. So again, I'm not supposed to publish anything which can be tracked. Any result that basically can be can be assigned to you, so this is not going to happen. And then date of birth. Also, it's not allowed. Okay, so just for the record, anything that reveals your identity, your phone number, your address, your date of birth, anything like that is not going to be allowed in this case. Not even parts of it. Okay, so just for you to know, there are always people who don't get this. I don't know why the reason. Okay, so, but anyway, so I will give you basically a personal identifier then. And I'm going to be very explicit here. Don't use basic empty spaces also, but please do not use the 7 dirty words, the 7 dirty words. I'm going to be explicit here, so apologize just for the record, because some people do. Okay, so the 7 dirty words are you can now use on TV in America, or fuck, shit, piss, tits, this and that. So, these are the words that you're not supposed to use, and not even in foreign language. Okay, so you guys told me that you're from Poland, right? So kurwa is also another word that I want to add, okay, just for you to know. Okay, but anything else, it's fine. I will Google them, so trust me, okay? So even if you try to test me on this, okay, whether this fits. Anyways, yeah, so the name of your PDF file, basically your first assignment should include your person identifier and assignment 1. That's important. Okay, so this is important, guys. Assignment 1, okay, so that should be basically included in the first one. So let's say you call yourself Mr. 123 or Mrs. 123, whatever. Then the PDF file should be named like this. Okay, so .pdf means basically this is the suffix, okay, of the file. You don't need to take photographs. Again, it's already uploaded. Everything is already uploaded, so you can check it out, the slides. But you can, of course. So I'm not basically preventing you from doing that. All right, is it clear, guys? Okay, so how to do it again, and you don't need to send any messages and all that stuff, so skip that part. Okay, so people say like, okay, dear Mr. Chernow, blah blah blah. I see it. Okay, so I see the attachment, guys. It's fine. Okay, so don't do that. Maybe you give me a subject, and that's totally fine. Okay, so if you send me an email, but anything else, so you don't need to polite nothing. Okay, so just send me it, and that's it. All right, guys, is it clear? Okay, so this is how to do it. Now, how does the assignment work? I want to basically give you information about that as well. So what's going to be the first assignment? We're going to talk about that in detail today. I apologize. There you go. Something is wrong. Something basically happened. All right, it's here. So that's going to be your first assignment. Now, what is your first assignment? And again, the topic of today is going to be that. The first assignment is going to be about a theorem which I'm going to introduce. This is going to be a transformation theorem. You need to calculate something, and you need 5 things to do that. So I'm going to give you the things that you will need. Okay, so the antiderivative, Stammfunktion, that's a German term. Antiderivative order is also the expression primitive function. I'll give you that one, so you don't need to, when you look at integrals, so I don't want you to calculate a specific integral. Okay, so that's going to be your assignment. But I give you the antiderivative, so you don't need to, you don't need to come up with the issue, how do I basically integrate the function that I'm supposed to. So I'm looking at the function x times e to the power of -1/2 times x squared. And the antiderivative of that is going to be, of course, with respect to x, is going to be negative e to the power of -1/2 x. -1/2 times x squared plus c, where c is a constant, of course. So that's the antiderivative, so you don't need to take care of that. Okay, so that's going to be hint number 1. Okay, you got this? If you differentiate this function with respect to x, then you're going to get that one back, okay, according to the chain rule. We might remember the chain rule, right? So you know how to do differentiation and stuff, but you don't need to confirm this. So this is basically what you see in blue is going to be the antiderivative of the green one. Is it understandable? All right, so that's number 1. So this hint number 1, so you don't need to basically, struggle with integrals and stuff, because if you have the antiderivative, the calculation of an integral, whether it's an improper or not, is going to be relatively easy. Okay, so that relates to the normal distribution, of course, as you might guess, okay, because the expression that you see here relate to the density of the standard normal distribution. Anyway, Second hint, okay, you need to understand what the absolute value of a real number is. Now people kind of struggling with that concept, but I'm basically need to define this. So the absolute value of a real number is going to be the real number itself if the real number is not negative, and it's going to be negative times x, okay, if you're basically looking at the absolute value of x, if x is negative. Now people are kind of struggling with the concept because they might suggest that negative x is negative. That's not the true, guys, okay, because if x is negative, then negative x will be positive then, okay, so you need to understand this. Now let me just give you an example. So for example, the absolute value of 5 is equal to 5, which is greater than 0, of course, and the absolute value of negative 2 is, of course, minus negative 2, and minus negative 2 is, of course, equal to plus 2, so you might understanding this right now. Okay, so this is going to be the absolute value because you need to break it down, guys. Okay, so you will need to deal with absolute values, and I want to give you the definition for that. Now, hint number 3, you need to notice that for a non-negative function, which is integrable, and it basically it doesn't matter whether the integral is improper or not. So if, I look at improper integrals, you know what improper integrals are. So when you have basically minus or plus infinity as a limit here, so you need to integrate from minus infinity to plus infinity. That's going to be a hint. And if you have basically a non-negative function, then you can simply just split the integral into two parts. For example, you can start by integrating from minus infinity to 0, and then you could basically add the integral from 0 to plus infinity, and if you basically just combine the two, then you're going to get the integral from minus infinity to plus infinity then. So this is what it's going to be. Again, so if it basically says it's an improper integral, then you have basically either plus infinity or minus infinity, for example, at some point. Okay, so these are 3 improper integrals, as you might see. All right, you need to have limits to calculate these. Okay, so you know how to calculate. You're supposed to have seen this before, I think, at least. So, but this is something that you can do. So you split that into 2 parts, and the reason for that is because the absolute value is involved. So then you can change basically how the absolute value is going to be then. Number 4, okay, so you need to know that the density of the standard normal distribution. This is something that you don't need to know, but I will give you the information. This is going to be 1 by the square root of 2 pi times e to the power of negative 1/2 times x squared. Okay, so that's the density of the standard normal distribution. Okay, and the density of the standard normal distribution, but that's something that you need to know, satisfies basically 2 things. Number 1, it's not negative. Everybody can see this. Okay, so this constant is not negative, and the exponential function is not negative either. And it satisfies also basically the other constraint, which is claiming that the total area of the density from minus infinity to plus infinity. This is what I'm talking about. So this improper integral is equal to 1. This is something that you would need to use during your calculations. Okay, so people kind of struggling with that, and then you would basically, this is something that you don't need to prove then. So if I give you these hints, this is something that you can use already. You don't need to take care of that anymore. Okay, so everybody knows that the total area of a density is equal to 1, including that of the standard normal distribution. So that's basically what you will have here. You don't need to take care of that. And then, of course, you need to recall that the expectation of a continuous variable is going to be, we talked about that yesterday. This is basically, if it has a density, of course, right? So, let's say it has a density, then this is going to be the integral from minus infinity to plus infinity of x times the density, right? So that's something that basically you already know. Now, what you don't know is that if you can apply a function on this, so let's say this is a type of regular function, that this is going to be the expectation of g of x, and the expectation of g of x is going to be simply just the integral of g of x times the density of function. So that's basically called the transformation theorem, which we're going to talk about. I will illustrate how this works in a discrete case, okay, but this is basically how it works in a continuous case. So for example, if you basically kind of struggling with that, but this is what you're going to see. Let's say you want to calculate the expectation of the square, okay, then basically you put the function, you put x into a function yielding x squared. So this is going to be x squared, literally speaking, times the density, and then you take the integral of that from minus infinity to plus infinity then. You understand what I'm saying? So if you have basically, let's say, whatever the function is, let's say you have the logarithm of x, then this is going to be the expectation of a logarithm. You might need this here and there, is going to be the integral of, let's say, ln of x times the density of x, not the density of ln of x, so you don't need to calculate the density of ln of x, guys. That makes it very practical in that sense. You simply just transfer the realization, let's say, basically of x, and you don't touch the density. So that's what the theorem is about, because this is not going to be affected by this. Okay, so that's what it is, all right? And you will need this, and this is called the transformation theorem. We're going to talk about that in a discrete case, so I will illustrate the transformation theorem today, but I'll basically give you an introduction. So if you put that into a function, you simply need to put x into the function. So you transfer, let's say, the realizations, but not the density. So the theorem is about not touching the density. You keep the density of x, and you simply just calculate basically the expectation of a transfer linear. I mean, if it's a linear transformation, then it's going to be easy. But if the transformation is nonlinear, okay, so then you can, most of the time, you cannot simplify this. So you need to multiply g of x, which is g is the function for the transformation, and multiply it by the density and take the integral of that. So these are the 5 points, and you're going to need all 5 of them. Okay, so because if you want to solve the task, okay, so this is what the task is going to be. So you need to find basically the expectation of the absolute value of a random variable, where the random variable is going to be a standard normal random variable. So if I give you the standard normal random variable and you calculate the expectation of the absolute value, keep in mind, guys, that if, of course, x is standard normal, then its expectation is going to be 0. So everybody knows this, right? So this is basically, I mean, straightforward. You can check that if you like to. But I'm not basically interested in the expectation. I'm interested in the expectation of its absolute value. And you need to show that this is going to be equal to basically the square root of 2 by pi then. Okay, so you need to play with the density a little bit, just as the way that I did it to you. I gave it to you. Okay, you can use the hints. So if you kind of feel like distracted and stuff, just look at the hints and that will help you. So this, you need to put the puzzle together, and that's going to be your first assignment. And the deadline is basically going to be next Friday. Okay, so next Friday, 11 p.m. So please make sure that you submit basically in time. All right, so I didn't mention before that you're supposed to submit in time, but I think this is straightforward to say. All right, so that's it. Anything else, guys? Okay, so questions related to that? Yeah. This is not a paper, so basically just, you know, this is just a little calculation regarding the integral which is involved in here, but the guideline of the paper, yes, sure. So when it comes to that, I will tell you how to write a paper and what's important, what's not, and what pay attention to and this and that, but it's going to be just a little. All right, so that's not a paper, this is just a, you know, a little, let's say, integral that you calculate. It takes about, let's say, 10 to 15 minutes. So if you, even if you kind of slow, don't worry, you know. So you need to just put these 5 things together accordingly. And again, I will illustrate how the transformation theorem works in a discrete case today, and you just need to apply this for the continuous case. Okay, so I'm not going to give you examples related to continuous case. I'm just giving you examples related to the discrete case, but basically for the continuous case, it works accordingly. All right, guys, so that's going to be it. It looks kind of difficult because you might ask yourself, okay, where is basically the square root of 2 times pi, 2 by pi, sorry, would come from? But the answer is because that's inside the density function of the standard normal distribution. So you have a little constant involved that you basically are getting rid of, and then you need to do improper integrals, this and that. All right? Again, if you're not able to edit formulas yet, just use basically handwritten notes, but I would like to ask you to just, you know, use the way that I was describing, because otherwise I can't read it. So if you submit, you know, a scan, whatever, a PDF of you take a picture with your phone and then you send it to me, it's not going to be readable if basically it's not the way that I described prior. All right, so keep that in mind, guys. I need to understand what you're doing, and yeah, I'm not able to if you don't follow the guidelines. Anyway, guys, okay, so that's that. All right, and are there any questions related to the first assignment? Again, I will illustrate the transformation theorem today, so that's going to be a topic of today. But other than that, this is basically what it's going to be. All right, I give you, again, so I will tell you what the assignment is, and next week on Wednesday, I will solve, I mean, basically, the week after that, because I have, you know, I gave you Friday, I will solve the assignment. Maybe post a video so then you can check it out what the solution would be, and so you can compare it to yours, and this is how it works. All right, guys, is it clear? Any questions? No questions? All right then, so I will basically continue. Okay, here it is. And here are the documents. So basically, this is the topic of today. I will continue from where I stopped from last time. All right, guys, this is going to be a second lecture then. All right, any questions? No questions? All right. Okay, then, yeah, let's move on. So basically what we're going to look at, I mean, I wanted to do it yesterday, but I didn't have time, unfortunately. So we'll look at the moments of linear transformations. Linear transformations are specific transformations of random variables, which are the most common ones. Okay, so if there is a transformation, it's mostly linear regarding random variables, but sometimes it's nonlinear. So if it's nonlinear, then basically we look at the transformation theorem, how to address that. Okay, so this is basically what's going to be. And I basically give you an introduction what it is. Then we're going to look at joint distributions, marginal distributions, and conditional distributions. The concept of conditional distributions is going to be very important in this course. Okay, so that is going to be a major issue here, especially conditional expectation and conditional variance. So but we're also going to look at theoretical covariance and theoretical correlations. Okay, so not the empirical ones, the theoretical ones, and then we can also address the theoretical one, I mean the empirical ones in time series, and then we need to find basically conditional expectations and a conditional variance. So if I say variance, I mean also conditional variance. Okay, so this is going to be a huge issue, guys. Okay, so especially the last one, and I would like it, I mean I want you to understand it. I will only consider the discrete case most of the time, because for the continuous case, examples are kind of, let's say, harsh, so over the top, but you simply just replace basically probability mass functions, whatever probability function you see, you simply just replace by the corresponding density. If it's basically the joint probability of mass function, then you replace it by the joint density. If it's a continuous, if it's a conditional probability mass function, you replace it by the conditional density. Although I must say the concept of conditional density is not straightforward, guys, especially for continuous random variables, because the reason for that is, of course, that if the random variable is continuous, then the probability that a certain, basically the random variable is going to take a certain value is always going to be 0. So the concept of conditional density is not going to be very straightforward here in this course. But the issue is that I don't have any means to define conditional expectations properly. So again, I will basically tell you what the missing part of the definition is. So for the discrete case, it would work, but for the continuous case, it doesn't. Okay, and I will illustrate why. But anyway, so this is a bachelor's course and not a basically PhD course, so I cannot address that issue properly. But anyway, so that will be fine basically just for you to give you intuitions. Now let's say you have a random variable. Okay, you know what the expectation and the variance is. So basically, this is something that you don't need to repeat. Okay, whether the expectation is, or whether the random variable is discrete or not, it doesn't really matter. You could basically calculate the expectation of either case though, and the expectation of a linear transformation is going to what we're going to look at. Now what is a linear transformation? You simply, so for example, you multiply the random variable by 2, so that's going to give you a little transformation of the random variable and add 5 to it, whatever that is. So if you do that, so let's say 2 times x plus 5, this is what a linear transformation would be. And in a general case, of course, you know, it's not just for 2 and 5, you can also do that for b. So you multiply it by b and add a to it, and a and b are constants there. So what you're basically generating here is going to be a linear transformation, and I basically want to recall what the expectation of a linear transformation is. Now the expectation of a linear transformation is, and that's simple, this is the linear transformation of the expectation. So you simply just basically take the expectation, perform a linear transformation on it. Now, of course, this is going to be the same linear transformation as the linear transformation for the random variable, and that's it. So you can take out the constants, whether they are additive or multiplicative, it doesn't matter. You can simply just take out the constants from the expectation operator. That's what I'm going to do, quite often, so, but you need to remember this. All right, is it clear? So again, that's easy to basically to demonstrate. I'm not going to, so because this is something that you should have considered in statistics. You should also have seen what the variance of a linear transformation is. So you have, again, you have a linear transformation, and you basically put that into the variance operator. Now keep in mind that the variance of a linear transformation is not, so this is not going to be the linear transformation of the variance. Some people basically claim that it is so, but that's not true. The variance of a linear transformation is simply just going to be, and how to do it is simple. You ignore the additive constant, and you basically take out the multiplicative constant by squaring it. So you have basically the multiplicative constant to the second times the variance of a random variable yielding the variance of a linear transformation. Okay, now first things first, okay, y is basically the variance of a linear transformation invariant with respect to the additive constant, so y is not there. And the answer is simple, because the variance is measuring distances of the random variable that it takes to its mean. If you increase the random variable by a, then the mean of the random variable is also going to be increased by a, so the distance will be the same. Okay, so that doesn't change. That's number one. And number two, y is basically squared. Okay, so y you would need to square the multiplicative constant if you want to take that out from the variance operator, and the answer is also simple. Just give you intuition. I mean, you can do this for yourself. This is not going to be an issue. The variance is simply the expectation of the squared distances between random variable and the expectation, right? So that's the reason. So if you basically consider that basically the linear transformation, the expectation of a linear transformation is the linear transformation of the expectation, and you take out basically the multiplicative constant from the expectation operator. You do the same thing basically for the random variable itself. So if you want to take that out from the variance operator, of course you need to square it, because again the variance is the expectation of the squared distance, okay, of the random variable to its mean. That's it. Okay, so this is the intuition, by the way. All right, so I want you to remember that. I'm going to use this in every lecture all the time. So all the time when I'm considering expectations of variances of so-called stochastic processes, for example, an AR process or stuff like that, okay, you're going to see this, that I'm going to apply this all the time. So this is basically my bread and butter, okay, in time series. I want you to basically to remember that. Okay, now, let me just give you the transformation theorem, how basically it is addressed. So if the transformation is not linear, then you cannot take that out from the expectation operator. So let me just give you basically what I mean. The expectation of a transformation is not going to be the transformation of the expectation in general. So this is not what it's going to be. All right, so this is not true in general. There are cases for which it is. For example, for linear transformations, it is true. Okay, so when you do the linear transformation, the expectation of a linear transformation is equal to the linear transformation of the expectation, but that is not true in general. So for example, when you look at the squares, okay, especially when it comes to the variance of a linear transformation is not the linear transformation of the variance. Now the question is how to address it, and the answer is most of the time you have to break it down in general. So we're going to distinguish between continuous and discrete random variables. So if you have just a simple okay, so there are restrictions involved regarding the function. So you cannot do this for any function, guys. There are restrictions, okay? One of the restrictions, but you could use for regular functions that you all know. So for example, logarithm, exponentiation, stuff like that, polynomials, this and that. So all types of regular functions, but there is a restriction that the function has to be Borel measurable. And you don't know what a Borel set is, and you don't know what basically Borel sigma algebra is, so I cannot basically address that question. But again, so if you want to, if you Google that, what's the expectation of a transformation, you'll find that there are restrictions involved regarding the function g that is going to give you the transformation. Okay, again, one of them is that it needs to be so-called Borel measurable, but you don't know what Borel sets are, so just ignore it. Okay, most of the functions that you're familiar with are going to work. Okay, so if there is some sort of abstract function here and there, that's something that you're not going to see in practice, so that's not going to be an issue. All right, so if basically you want to know what the restriction is, go to my PhD class and I will explain it there. Okay, but anyway, so if you want to break in, let's say you want to calculate the expectation of a transformation, we're going to distinguish between the two cases, right? So first case is that if x is going to be discrete, now that's going to be simple. All right, so if it's discrete, and this is what I'm going to illustrate, the expectation is the sum with respect to the realizations. You have basically the weighted sum of the realizations, each of them weighted by its corresponding probability mass function. Okay, so that's what you have learned. So this is the expectation of a random variable. So that statement is not true yet because you don't transfer it yet. Okay, so if it's no transformation, that it is true. However, it's enough to transfer the realizations only. So you don't touch the probability mass function. You transfer the realizations only. Okay, in this case, if the random variable is discrete, that's relatively easy to prove, okay, so that is true, because if you apply a certain transformation on the random variable, you could also reverse it, okay, so then the equality basically would still be true. So that's not going to be an issue. All right, so that's number one. Number two, however, the second one is going to be a little bit more difficult to prove, but that works similarly. So if you want to calculate the expectation of a continuous random variable, I repeated this already, this is going to be, let's say, the integral of the realization times the density with respect to the realizations, okay? So if you have something like this, you have no transformation yet, so that statement is not true, what you see right there. Now this is true, okay, so the expectation again of a continuous random variable is looking like this, but also for that one, it's enough to transfer the realizations only, so you put the realizations basically into the function g, and then you multiply it by the density, and you take the total integral of that, and this is what it's going to be. All right, guys? So this is how it works. I mean, the approach is quite similar, okay? So you simply replace the sum by the integral, and you replace the probability mass function by its density, okay? So although the notation is similar, keep in mind that depending on the context. So if the random variable is discrete, fx is going to be its probability mass function. If the random variable is continuous, then fx is going to be its density. All right? I assume it has a density, so just for the record. All right, guys? Is it clear? So again, we did this last time, and basically this is an extension to this, and this is a generalization. Okay, so if the transformation is linear, then again, you can take it out from the expectation operator, because the expectation of a linear transformation, as I said before, is a linear transformation of the expectation. So that's that. All right, guys? So now I'm going to show you how this works basically for the discrete case, and for the discrete case only, that's quite straightforward. Okay, so let's say you have a discrete random variable, and this is the, the distribution of it. Okay, so this is the same example as I did basically yesterday, so I'm picking the same example. I'm going to do that today. And the expectation of x was, and you might remember this, the expectation of a discrete random variable is always going to be the sum of its weighted realizations, each weighted by the corresponding probabilities. So you simply just take the realizations, okay, and then you multiply them by the corresponding probability. Now, if you want to take the expectation of the square, okay, so then you need to take the square of the realizations accordingly. So this is what it's going to be. So I'm saying 1 squared is basically the first realization of x squared, because you take the realizations of x squared, right? So that's it, okay? So 1 squared times the probability of 1 plus 2 squared times the probability of 2 plus 4 squared times the probability of 4, and that's it, because there are no more. Okay, so the random variable in this case has no more realizations. So this is going to be, now you can take your calculators, and if I did it correctly, the expectation is going to be 4.9. Is it understandable, guys? So you only, if you want to take the expectation of a transformation, whatever the transformation that is, and if the random variable is discrete, then all you would need to do is just to transfer the realizations of the random variable and to keep the probabilities as they are. Okay, so that's what the transformation theorem is about. Okay, so this allows you basically to address, higher moments of random variable. For example, this is the second moment, guys. Okay, so the second moment was 4.9. I can't recall what the first moment was, but that was basically the weighted sum of the realizations, each weighted by the corresponding probability. All right, I think it was 1.9 or something. Yeah, but this is true. All right, so this, again, doesn't matter. All right, is it clear? So that's the second moment, guys. So the transformation theorem allows you to calculate higher moments of random variables, among others. All right, because that works for every function that you know. I mean, I assume. For example, for polynomials, it's going to be fine. And you need basically just that. Now, if you want to take, for example, the third moment and the expectation of the third, this is the third moment of the random variable, all you would need to do is just to transfer the realizations accordingly. So it's going to be 1 cubed, right, plus, times its probability plus 2 cubed times its probability of 2, right, plus 4 cubed times the probability of 4. And this is basically done accordingly. So this is going to be, if I did it correctly, 15.7. So that's the third moment of the random variable, guys. Is this understandable now? So if you take the fourth moment, right? So this is basically done for calculating the kurtosis of the random variable, so you would need to have the fourth moment. The fourth moment, so which is the expectation of x to the fourth, is going to be the realization to the fourth, each realization to the fourth, times the probability of the corresponding realization that you were transferring. Okay, so again, what's important here to note is that the probabilities don't change, and neither does the density if you perform a transformation on the random variable, whatever the transformation would be. All right, so you can also use it for basically for the logarithm if you like it. So if you take the logarithm of x and you want to calculate the expectation of a logarithm, this is going to be the weighted sum of the logarithms of the realizations, each weighted by the corresponding realization. That's it. Is it clear, guys? Okay, so you can use it for almost every function that you know, I think. All right, so there are some functions that you cannot use it for, but other than that, this is what it's going to be. And in this result, this is going to be the logarithm of 2 to the power of 0.7. All right, so that's the expectation of a logarithm, guys. Is it clear how it works, the transformation theorem? And then, of course, in the continuous case, it works accordingly. And then you would need to use this as part of your first assignment to use that for the expectation of the absolute value of a standard normal variable. All right, so that's that. Okay, again, so check that out, guys, and submit your results. I'm expecting them. All right, now I'm going to continue with the joint distributions. All right, so this example is related, I mean, it was my example that basically people took for statistics for the bachelor's course. Okay, so I brought this example with me from Heidelberg. I remember me working in Heidelberg, and I was conceptualizing it there. So, but it doesn't matter. So it was basically considered, and it was too late for me to realize it. But anyway, so let's say I have, okay, so I will just change the distribution of the random variable that I'm going to consider. So it will have the realizations -1, 0, and 1. Okay, so you would put the probability mass function at these points. Okay, and every single realization is going to be, you're going to have the probability of 1/3. Okay, so you can also call it the discrete uniform distribution if you like, but in general, the discrete uniform distribution is not having negative realizations, but it doesn't matter. So it could be a transformation of a discrete uniform distribution anyway. So in general, it's not going to be what it is. Now anyway, so this follows basically discrete uniform distribution on the support -1, 0, and 1. Okay, so it's discrete because there are no other realizations. And then let's say you create another random variable, which is going to be the square of x. Okay, so this was x, and then you have y. And then, of course, y can only take two values, namely 0 and 1. How come? Because, you know, if x is equal to -1, then y is equal to 1. If x is equal to 0, then y is equal to 0. And if x is equal to 1, then y is equal to 1. And there are no more realizations. So y will have just basically two realizations. And these will have the following probabilities. If y is equal to 0, then of course, if x is equal to 0, then it's going to be y is equal to 0. So this is going to be equivalent, right? So that means that the probability of y being equal to 0 is going to be 1/3. And for the other realization, it's going to be 2/3. So yeah, that's it. So I think this is going to be understandable. Again, assume that this is given. So what you see in the yellow box is given, and everything else is basically added to the example. All right? So, but that's something that you need to come up with. Is it understandable? Now I want to look at the joint distribution of the two, because this is something that I didn't address. These were the marginal distributions. And the joint distributions are going to look like this. So if you have something like this, for example, you want to find the probability that x is equal to -1 and y is equal to 0. This cannot happen, of course, so simultaneously. If y is equal to the square of x, then this is not going to happen. So if x is equal to -1, then y must be equal to basically equal to 1, so that's not going to work. So y cannot be 0 and x cannot be -1 at the same time. So the probability for that is going to be 0. That's easy to grasp. You understand that? Okay, so what about that one? If x is equal to 0, then y cannot be equal to 1. So the probability of that both are equal to, that x is equal to 0 and y is equal to 1. So if I say joint distribution, that means both. Okay, so that means the term and. So this means x is equal to 0 and y is equal to 1. Okay, so that cannot happen, of course. All right, so you need to understand that. And if x is equal to 1, and then you cannot have y being equal to 0 then. So that should be also clear. So these probabilities are 0. And you need to fill out basically the empty spaces, of course. So you can basically use the fact that the sum of the joint distributions are going to be equal to the marginal distributions. This is a statement that I didn't address yet, but I think it should be straightforward. So the probability that is missing is going to be 1/3, which is here, and the probability for that is missing here, so for the empty space, is also going to be 1/3, because again, the sum of the joint distributions, if you sum them up accordingly, is going to be equal to the marginal one. So, and you have these on the margin, so That's that. And here is basically the point missing 1/3. Is it understandable? So again, this is an easy example. You're not going to see anything like this, but I wanted to recall what it would be. So what you see inside here in this rectangle is going to be the joint distribution of the two. So this is actually the joint probability mass function of x and y. You need to specify that, for example, in order to calculate the expectation of a product. Okay, so if you want to know what the expectation of a product is, you need to know what the joint distribution of the random variables is going to be. Okay, because other than that, you would not be able to address this issue. All right, so that's something that I wanted to basically stress here. Now let's start with the expectation of x. The expectation of x, again, as I said before, since x is a discrete random variable, is going to be the weighted sum of its realizations, each weighted by the corresponding probability that you see in the margin. Okay, so this is the marginal distribution, or simply just a distribution of x. So you take that and multiply it basically by the corresponding realizations. The realizations are here, so if you want to basically just do that, this is going to be -1 times its probability, right? So then plus 0 times its probability then, and then you have basically 1 times its probability, and you need to sum up these, and that's going to be the expectation. Now, as you see, the expectation of that is equal to 0. Everybody sees that? Okay, so that's easy. Again, this relates to the concept yesterday, and that's also going to be similar for y. So if you take the expectation of y, you do the same thing. You take the realizations of y, and each of them is going to be multiplied by its corresponding probability, and then you create the weighted sum of that. So it has basically just 2. I mean, you could skip the zeros, but I do it anyway. 0 times its probability, right? This is it, plus 1 times its probability, and that's going to be it finally. So this is going to be 2/3. All right, is it clear, guys? Okay, so this is the expectation of, let's say, the marginal, random variables using the marginal distributions. That should be understandable. And then, of course, if you want to take the expectation of a product, you need to join distributions. Because the statement, since basically x is discrete and y is discrete, their products is going to be discrete all the time. So the number of realizations is going to be countable. Now the issue is, how many realizations do you have regarding the product of the two? So you need to take, this is also going to be the sum of the realizations, basically weighted, where the realizations are going to be weighted by the corresponding probabilities. In general, if x has 3 realizations and y has 2 realizations, then the product of the two is going to have 6 realizations. So because that is equal to 3 times 2. Okay, so the number of realizations is going to be equal to basically, in general, of course, you're going to have some that are going to be dismissed because of the zeros, but in general, if x has 3 realizations and y has 2, then the product will have 6. Okay, so you need to basically consider all 6 of them. Now the issue is that basically these realizations happen simultaneously. You would need to take the corresponding joint probabilities to address that. So if x is equal to 1 and y is equal to 0 again, but this is not happening, the realization is going to be that, and y is not happening because the probability of that is going to be 0. So again, the procedure is the same. Each realization is multiplied by its corresponding probability. The only difference is that I need to take the joint probabilities basically if I want to address the expectation of a product. Got that, guys? Okay, so this is what it's going to be. Now again, the second realization is going to be the product of the two, but again, so this occurs basically with probability 1/3, and then you have basically the third realization, which is going to be 0 times 0. Then of course some of the realizations are equivalent, but this is not true in general, so I wanted to basically do that in detail, times its probability. You could skip it actually, and then of course you have the product of that two, which is basically not happening almost surely, right, because it has a 0 probability, of course. And then this will not happen either, okay, because it has 0 probability. And then the last one will have probability of 1/3, guys. Do you understand the concept here? Again, so keep that in mind. This is very important. If you take the expectation of a product of 2 random variables, you need to have the joint distribution of the two in general. Is that correct? All right, so yeah, that's it, and then you can take your calculators. This example, this is of course relatively easy because, you know, this is 0, this is 0, this is 0, this is 0. So that's what you're left with. And then you find basically that the expectation is 0, of course, right? But that's just a side note. That's not important. All right? It could have been also something else. It doesn't matter. Is it clear, guys? All right? Now, all right, so I want to have basically that summarized regarding the expectation of a product. So the expectation of a random variable, if it's discrete, is going to be, again, its weighted sum, where the sum ends are going to be weighted by the corresponding probability. And then if you have another where you would need to basically calculate the expectation of a product, then you would need to just basically summarize or basically sum up the corresponding realizations by using the joint distribution instead, or the joint probabilities, which I basically was introducing to. All right, this is it. So the joint probability is expressed by, you know, this expression. This will be, so it's just for you to see. So if you have, you know, x and y, which are the random variables at point, if you have basically at point x and y, okay, this is going to be the probability that x takes the value small x and y takes the value small y. So that is going to be the joint probability then. Do you understand that? Okay, so that's just a different notation. Because, again, if you want to have that for a continuous case, if x and y are going to be continuous, then you simply just replace the joint probability mass function by the corresponding joint density. This is how you refer to it. Okay, so if you want to check that out, you can take, for example, the multi-dimensional normal distribution for that. But again, examples related to joint continuous densities are not very straightforward as a discrete case, so I'm going to skip them. That's not that important for time series, but you need to understand what this is about. If the random variable x is continuous, then you simply just use x times the density, and you take the total integral. You've seen this before. And if you want to basically, you know, address the question, how would you calculate basically the expectation of that, so the expectation of a product, because this is what we're going to look at, then you need to have the double integral, and then of course you have the joint density involved. So the first integral relates to x, so you can also split into two parts if you like. You don't need to, but you can also look at it this way. So you integrate with respect to x first, and then after that you integrate with respect to y for then a second. So this is how it's going to be. Is it understandable? All right, so again, maybe I drop some examples here and there, but again, so the examples related to joint densities are not very straightforward. Okay, you can check out the joint density of the basically of the normal distribution, so the bivariate normal distribution if you like to. All right, now I want to provide you with another definition, which is a covariance, where you would need exactly that. So the covariance of two random variables is going to be the expectation of a product. So you can see over here, so the covariance requires the joint distribution y, because the expectation of a product, so if I say product, I mean that's going to be the first random variable inside, and that's going to be the second random variable inside. And each time you calculate the expectation of a product, you need to have the joint densities, guys. All right, so automatically the covariance requires that. Now the first product is going to be the difference of x to its mean, and the second the first factor of the product, is going to be the difference of x to its mean, and the second factor of the product is going to be the difference of y to its mean. And if you take basically the expectation of that product, this will yield the covariance. As you might know, the covariance is a measure for linear relationship between two variables. Okay, so you can only address linear relationships, but no other. This is going to be equal to, and if you know what the properties of the expectation operator are, you have the expectation of a product minus the product of the expectations, which is a more easier one. All right, so again, expectation of a product is going to be here, and minus the product of the expectation. This is the most common formula. But again, anyway, you need to have the expectation of a product still. So you could not get away with the joint distribution in general. Is it understandable? Now we have addressed how to calculate the expectation of a product using joint distributions, at least in the discrete case. So I want to basically, you know, sum up these results, which basically you have seen before. Now, before I do so, the random variables are said to be uncorrelated if their covariance is equal to 0. That's basically it. Okay, so if the covariance is going to be 0, which is going to be the case, by the way, in the discrete example, then the variance are said to be uncorrelated. So the correlation is going to be also 0, because the correlation is based on the covariance. So if you want to address the correlation, this is going to be the covariance divided by the product of the standard deviation. So you have the standard deviation of x first, and then you have the standard deviation of y as second, and then you multiply the two, and you take that and you divide that by the covariance. Oh, you divide the covariance by that, sorry, this way around. And then you're going to get the correlation. This is the theoretical correlation. I didn't calculate the variances in the discrete case because I was too lazy for that, but you can check it out. I mean, this is, you know, another example which we did yesterday. So yesterday's lecture would tell you, illustrate how to calculate at least the variance of a discrete random variable, and you would need to do that accordingly when the random variables are continuous. I only consider the cases where, guys, where either both are discrete or both are continuous. Okay, because let's say if one is discrete and the other is continuous, this is not very straightforward either. But in practice, you would don't need that anyway. So I never basically had a random variable where one is going to be following the normal distribution and the other is going to be binomial, and then there is a relationship between the two. So I didn't basically have seen this before. And again, at least in applications though. So especially not in time series. So you would not get that. Now, anyway, so you need to know that the correlation is always going to be between -1 and 1. That's something that you might know. If the correlation is either 1 or -1, then this means that one variable is always going to be a linear transformation of the other. So keep in mind, if the correlation is 1 or -1, then the random variables are going to be linear transformations by each other. If y is a linear transformation of x, then x is also a linear transformation of y. This is a one-to-one relationship, guys. So if you are married to someone, that person is also married to you. Understand what I'm saying? So that's it. Okay? So, and this is also true for linear transformation. So again, if basically y is a linear transformation of x, then x is also going to be a linear transformation of y with different coefficients then. All right? Is it clear? So that's something that I wanted to mention here. So if there are linear transformations of each other, then the correlation is either 1 or -1. And if the correlation is either -1 or 1, then there are linear transformations of each other. So this is also a one-to-one relationship, guys. Okay, so that's something that you need to understand. Now, again, so I wanted to have that summarized. So let's say y is a linear transformation of x. So this also automatically implies that x is a linear transformation of y. So then, of course, the correlation can only be basically two different values. Of course, if it's equal to 1, if basically the parameter b is positive, and it's equal to -1 if the parameter b, so the slope coefficient. So I call this a slope coefficient, guys, because if there's a linear relationship, this is going to be the slope, right? And so if the slope coefficient is negative, then the correlation of the two is going to be -1. So if one is a linear transformation of each other, then the correlation cannot be other than -1 or +1. Is it understandable? Now, if you can argue that basically if b is equal to 0, then then the correlation would be equal to 0 then. Okay, so I'm not basically content with that, but the issue is if b is equal to 0, then the random variable is still going to degenerate to a constant, so it has no variance, so that's going to be an issue. So you cannot express the correlation of that because it has no variance. Or it has no variance is wrong. It's going to be degenerating to a constant, and there is no random variables anymore. So nobody is basically considering that. Anyways, okay, so that's something that I basically wanted to address. Now, let's go back to the example. I'm going to address what the covariance is because we have the building blocks for that. So the expectations were expectation of x, expectation of y, and the expectation of a product of x and y, again, were 0, 2/3, and 0 respectively. And then these are the blocks for the covariance, because the covariance of the two is going to be the expectation of a product minus the product of the expectations. Okay, so then you simply just plug in, and then you're going to get 0. If the covariance is 0, as you see, this is a simple example, then you could conclude that the random variables that are involved are uncorrelated. Okay, uncorrelatedness means that there is no linear relationship between them. But keep in mind, guys, and this is basically the danger, so that's why I was conceptualizing this example, because I wanted to illustrate something. Just because random variables are uncorrelated, it doesn't mean that they are independent. Okay, so the major problem with this measure is that it cannot detect any other relationship, any relationship other than the linear one. Okay, so you cannot address any other relationship regarding this. Okay, so just because random variables are uncorrelated, it doesn't imply that they are going to be independent, because there is a dependency. Okay, so there is a dependency still. You understand what I'm saying? If they are independent, I will define independency later, not now. But if they're independent, that's simply going to be that the basically their joint cumulative distribution functions is going to be equal to the product of the marginal distribution functions. But I'll come back to that later on. If they're independent, then they're going to be uncorrelated, because if there is no relationship between them, there is no linear relationship between them also. Okay, but if there is, just because there is no linear relationship between them, it doesn't imply that there is no relationship between them at all, as this example basically suggests. So that's the reason why I wanted to conceptualize that. Again, the covariance as a measure, basically measuring linear relationships only, okay, has an issue that it cannot detect in general any other relationship other than the linear one. Is this understandable? So whether it's empirical or theoretical, it doesn't matter. So just because, you know, let's say when it comes to empirical correlations, just because, you know, random variables don't correlate with each other at the 5% level, so let's say you want to test this, okay, it doesn't, you cannot conclude there is no dependency based on that at the 5%. No independency, you cannot say that they're independent at the 5% level even. Okay, so if you even if rejected the corresponding null hypothesis that there is no correlation between them. Is this understandable, guys? Okay, so please, I mean, keep that in mind. Okay, so or you don't reject the null hypothesis. Sorry, that's the word. So if you don't reject the null hypothesis, meaning that they are uncorrelated at the 5% level, that does not imply that they are independent at the 5% level. Okay, so please be careful regarding this. But that's the issue. So what am I supposed to do then? Okay, I cannot basically do that one. What you can do is, of course, you can transfer one variable, and then you can examine the correlation between the new random variables. Okay, so new pair, and then you can say. Anyway, okay, so that's something that I'm not going to discuss here, but you need to understand that just because they're uncorrelated, it doesn't necessarily mean that they are independent. In this case, this is not true. All right, so that's why I wanted to have that included in here. All right, now regarding the covariance, I want to also address what the covariance of a linear transformation is. Okay, so you want to basically calculate the covariance of linear transformations. So you perform a linear transformation on X, and then you also perform a linear transformation on Y, okay, which X and Y are the random variables that are involved. And the question is, what's going to be the covariance of the linear transformations? Now, similar to the variance, the covariance does not depend on additive constants. So you can simply cancel basically A and C. So you can, and then you take out basically the multiplicative constants out of the covariance operator. I'm going to use that one also quite frequently, guys. Okay, so simply just take out the multiplicative constants from the covariance operator and ignore the additive one, similar to the variance, okay, because the covariance also measures expectations of a product of the distances of each minus its mean. So if you increase, let's say, basically if you increase, let's say, the random variable X by A, then the mean is going to be increased also by A, so the distance between X and its mean is going to be the same, even in the new case. All right, so it's just basically the same as in the previous one. That's why the covariance does not depend on additive constants, but only multiplicative constants, and the same is true also for the random variable Y. Is this understandable, guys? So that's what I basically wanted to mention here. Yeah, and I would like you to know this. So yeah, and then of course, if the random variable is discrete, then I'm going to look at the expectation. Now, again, you might know what the expectation was, and based on that, I'm going to give you the so-called conditional expectation, but not now. So the expectation of X, again, we said it before, and I'm going to say this for the last time, is equal to the weighted sum of its realizations, each weighted by the corresponding, you know, probability mass function or the corresponding probability. Now, if I look at so-called conditional expectation, and that's what I'm going to define here, or basically illustrating that, we look at the expectation of X given a certain condition. So given Y is equal to, let's say, small y, what's going to be the expectation of X? I will give you an example to that. But the only thing that you would need to replace here from the regular expectation, so this is the unconditional one, all right? So that's the unconditional expectation that you see, okay? And if you want to address the conditional one, you replace basically the probability mass function by the so-called conditional probability mass function of X. That's it, okay? So the conditional probability mass function, which I'm going to define below, is going to be, and this is what you see here, so the probability mass function of X conditioning on y, this is the notation, is going to be, and this is what it is, here down there is going to be the ratio of the joint distribution divided by the probability, or divided by basically the probability mass function of the condition. That's it. So this is basically what it's going to be. All right, so you take the joint distribution divided by the marginal distribution to get the conditional distribution of a random variable. Okay, now if it's discrete, the definition is straightforward. Okay, if it's continuous, it's not. I will basically address the issue why it's not very straightforward what I'm doing. But I cannot go beyond that because the problem with that is that this is going to be, relatively complicated, let's say. So if both are continuous, okay, then it's going to be basically done accordingly. Again, let's recall what the expectation of x is. The expectation of x is basically the integral of its realizations time its density. Okay, so if it has a density, I assume it always has a density, all right, so because most continuous variables do. All right, so this is basically what it is. Now, if you take the conditional expectation, you just simply replace it by the conditional density, and this is defined accordingly. So conditional density is going to be the ratio of the joint density divided by the marginal density, as you saw. Now, the issue with that is the following. So the problem if x and y are continuous, especially if y is continuous, so that is even basically more important, okay, then the probability that this is going to happen, so the probability that y is equal to a specific value is always going to be what you might remember this. So if basically y is continuous, then the probability that this is going to happen, it's not going to happen almost surely, you say, but the problem is that this is going to be equal to 0. And if this is equal to 0, again, so if the random variable is continuous, no matter what y is, so it doesn't matter what y is, then what you have is, of course, you have a 0 probability there, so this is not going to work in this case. You understand what I'm saying? Of course, just because it's equal to 0, that doesn't mean that the density is 0, right? So, but that's not going to be straightforward because this is called the null set, okay? So if basically an event has 0 probability, is going to be called the null set, okay? So that's the so-called null set. So if you have a null set, it's not straightforward basically to define conditional expectations of continuous random variables the way that I did. You understand the issue? So there's a contradiction in the definition, guys, okay, because it's not going to work. And I cannot dissolve the contradiction unless I define conditional expectations properly. But if I define conditional expectations properly, you're going to skip this course, trust me, because that is, okay, that was a pain. That was very painful even for me. So I remember me being a student back then, and I saw the definition of conditional expectations, conditional expectations here, the general definition. So it was very, very painful for me, so that's complicated. Okay, so I needed basically 1 or 2 weeks to remember just to understand what the definition is. And I don't have time for that. So, but you're going to not need this anyway in time series. So this is just the beginning, right, guys? Okay, so if you want to continue with your studies, then I could basically address conditional expectations for continuous variables properly. So, but that's not going to be. All right? But again, if you apply it, this is how it works. Anyway, is this clear, guys? Okay, so again, I apologize, but the course structure does not allow me to do this. Okay, so that's also the reason why I only consider basically the discrete case an example only, because that's much, much easier than the continuous case. And you don't need it in applications anyway. So I want to also focus on applications. Of course, I would need to back up with the theory, but only basically for the purpose that you will go to apply it properly. So, and you also, I would expect basically to understand that. All right, so again, I apologize. This is not going to be basically very straightforward here regarding continuous variables, but again, I have no choice, okay? So you need to have, let's say, 1 or 2 more years to add to your bachelor's degree, and then we can talk about it. All right, maybe I shoot a video about this at some point. Anyway, so let's consider what the variance or the conditional variance is. You might remember the variance was, and again, this was also illustrated, the expectation of the squares, or the square, let's say, minus the square of the expectation. And if you take the conditional variance, you simply just replace the unconditional expectations by the conditional counterparts. So you have the expectation of the square basically given the other event, right? So then, which is basically the condition minus the square of the conditional expectation. That's it. All right, so the conditional expectation of the square minus the square of the conditional expectation will be the conditional variance. I did not do this, okay, so maybe you could add to the example with the table. All right, so you could basically calculate as an exercise the variances, and then you could also address what the conditional variance is or would be. But keep in mind, I will come back to that later on. Conditional variance is going to be a very important concept in this course, especially related to time series, especially when you look at so-called Arch processes. Okay, so I'm not going to tell you what Arch is, but the acronym stands for autoregressive conditional heteroscedasticity, and conditional heteroscedasticity means that the conditional variance of the process is going to be time dependent, guys, although basically the unconditional variance would not be. Okay, so even if the unconditional variance of the process would not be time dependent, the conditional variance of the process can be time dependent. So I will come back to that concept, and this is going to be a huge issue in this course. Okay, so that's why this is very, very important, guys. Okay, but anyway, you just need to remember that, again, I repeat, the conditional variance is equal to the square of the conditional expectation minus the other way around. So the expectation, the conditional expectation of the square, that's it, minus the square of the conditional expectation. That's it. Okay, so the conditional expectation of the square minus the square of the conditional expectation is going to be the conditional variance. Maybe you could, solve the example where you would calculate the conditional variances. I will come back to basically the conditional expectation in a moment, but for the conditional expectation, you need to have the conditional distribution. All right, so if you want to address the conditional distribution, let's say, of y given x, I was flipping the formula, so given basically the case that x is going to be equal to 0, given that, you need to basically do what to do to get this. You need to find the joint distribution. I mean, you have the joint distribution inside the table, so there is a formula. You simply basically take the joint distribution or the joint probability related to it of this event, guys, of course, which is here. So that's the probability of this event divided by the marginal distribution, okay, which is here of this event, because that's the probability of the condition. So the joint distribution divided by the marginal distribution, let's say, straightforwardly, is going to be the conditional distribution. And you do this basically given the condition that x is equal to 0. So in this case, this is equal to 1, of course, and then the probability that y is equal to 1 given x is equal to 0 is going to be 0. Why? Because the joint probability is equal to 0. Okay, so the joint probability divided by the marginal probability, it doesn't yield anything other than 0. Okay, so that's going to be what you see here is the conditional distribution of y given x. Again, you might recognize I was flipping basically the formula because I was defining the conditional distribution of x given y, but I will basically look at, in this case, the conditional distribution of y given x being equal to 0. Is this understandable? Now, if you want to keep that in mind, guys, so I want you to remember that, because I will need to calculate the conditional expectation of y given x is equal to 0, and I would need those. Okay, so I would need these probabilities, not the unconditional ones. Okay, so you need to replace the unconditional probabilities that you saw by the conditional ones. Okay, actually the unconditional probabilities, let's call them unconditional probabilities, are here, but that's not the ones that you use. Again, I said before, and I'll say it again, the expectation of a discrete random variable is this weighted sum of its realizations, each weighted by the corresponding probability. But this time, since it's a conditional expectation, you need to weight them by the corresponding conditional probability. So y times its conditional probability, which was equal to 1, as you saw. Okay, so y being equal to 0, basically times the conditional probability of that, plus y being equal to 1, which is 1, realization, times the conditional probability of that, which was basically 0. So the conditional expectation of 0, just for you basically as a comparison, the unconditional expectation, if I recall this correctly, was 2/3. All right, so that's that. So the conditional expectation can be different from the unconditional expectation. This is also an indication for dependency, by the way. All right. Is it clear, guys? Okay, so this is what we do now. This is going to be very major, very important concept. Now, I want you to stress, the following issue, because conditional expectations can be random and can be constants, okay? So assume, for example, that y is a linear transformation of x, and this is the particular linear transformation that you consider, and then we want to calculate, let's say, the conditional expectation of y given x being equal to 2. Now, in this case, you don't need to have the conditional distribution of y because you already have the relationship between the two. So what you do if you have something like this, okay, so if x is given, which you basically can see here, the issue is you can simply take it out from the expectation operator. So anytime basically you have a conditional expectation regarding a random variable which is supposed to be given, you can take that out from the conditional expectation because in this case you already know that it's going to be a constant. So x is a constant already, so therefore any linear transformation where x is involved is going to be a constant also. So and the expectation of a constant is going to be the constant itself. But again, let's do this step by step. So what is true for unconditional expectations is also true for conditional ones and vice versa. So when it comes to linear transformations, whether the expectation is conditional or not, it doesn't matter. You can simply take out the linear transformation from the out of the expectation operator because the linear transformation of the expectation, whether conditional or unconditional, is going to be the transformation a linear transformation of the expectation, right? So the expectation of a linear transformation, whether conditional or unconditional, is going to be the linear transformation of the expectation. You see that, guys? Okay, so now again, so what's going to be the expectation of x is if x is equal to 2. So given x is equal to 2, what's going to be the expectation? Now that has no more expectation because it's already a constant. So this means that you're going to get 1 plus 2 times 2, which is equal to 5. So keep in mind, and I wanted to stress here, that the conditional expectation, this one, okay, if x is specific. So if x is specific, then the conditional expectation of y is going to be a constant if basically y is a linear transformation of x. You understand this? Okay, and if it's another transformation, that is also going to be a constant. So this is not only true for linear transformations, but in this case, I will use this for linear transformations in particular. You understand that, guys? Okay, so keep in mind this is a constant then. Okay, so conditional expectation is a constant, all right? But in general, it is not, because if x is not specific, as this is the case, okay, so if you look at the conditional expectation of y, given x, so this is another concept, this is going to yield a random variable. I want basically to explain that. So when you do just simply, expectation of a linear transformation is going to be the linear transformation of the expectation, whether conditional or unconditional, it doesn't matter. Now, what's going to be the expectation of x? Given x, now of course x is given, then the expectation of it will be simply just x. So you can take out anything from the expectation operator that is given. So if it's a random variable which is given, then take that out. So this is what it's going to be. Now, as you see, this expression here is not a constant. This expression is a random variable. Okay, so you need to be basically careful, guys. This expression is then, this means that it's a random variable. It is, of course, equal to y. So in this example, as you see, okay, so what you see here is equal to y. So the conditional expectation will be equal to y then, in this case. So you might argue that the conditional expectation of y is going to be equal to y. However, this is not true in general. So in general, you don't have that, although this is going to be basically in this case. So in general, basically, this is not true. Okay, however, there is exceptions to this. All right, is it clear? Okay, so there are exceptions to this, as this shows. So if y is a linear transformation, then it's going to be equal to its conditional expectation. But if it's not, then it's not. Okay, so then don't confuse the two. But in this case, it is. Okay, so in this example, it is. But it doesn't matter. I wanted to show you that this is a random variable, and therefore, we must treat it as such. And this is basically what, for example, the next theorem is going to be based upon. This is the law of iterated expectations, one of the most important theorems in econometrics as well as in time series. This addresses basically how you can calculate unconditional expectations, because the unconditional expectation of a random variable, according to this, is going to be equal to the expectation of its conditional expectation. Keep in mind, so that's basically the statement, the unconditional expectation of a random variable is going to be equal to its expectation of the conditional expectation. Keep in mind, but just because you have that, okay, you cannot conclude, so this does not imply, and then again, so I wanted to stress this, this does not imply that y is equal to its basically its conditional expectation. So just basically because the expectation of both sides are equal, it doesn't mean that the random variables are equal. Understand what I'm saying? Of course, if y is a linear transformation of x, then it is going to be equal. Okay, but it's not true in general. So in general, y, again, I mentioned before, is not going to be basically equal to its conditional expectation. But sometimes it is. Okay, so there are cases it is, especially when it comes to linear transformations. You understand it, guys? But I wanted to mention here, this is a random variable, so you could basically, theoretically speaking, you could calculate its expectation. And you will find if you take the expectation of that random variable, this yields the expectation of y, which is its equal to its unconditional expectation. And this is what the law of iterated expectation claims. Okay, this is a very important theorem, guys. Okay, maybe you could, you would address the proof, but you need to be careful when it comes to the proof because there are lots of errors that I discovered. Okay, when you Google that, so some people will say, okay, so that was an assignment last year. I remember that. So basically, I was giving, the issue, prove that when x and y are discrete. Okay, and people were Googling it. The proof was wrong because they didn't consider the fact that the conditional expectation is a random variable, guys. So it's not specific. Okay, so x, which is the condition, is not specific, and you need to treat it as such. Okay, so there is errors in the proofs that if you Google them. I'm not going to fix them. Okay, so it's not my job to fix the internet, guys. You understand what I'm saying? But people do it basically wrongly, just for the record, because they don't consider the fact that the conditional expectation here, expectation of y given x is a random variable, and you need to be very careful how to calculate basically those things regarding the notation. So you're not supposed to switch to a specific one. That was a mistake that a lot of people made last year, and in assignment. So yeah, I want basically to just remind you of that one. Okay, so again, two things. Number one, the conditional expectation is a random variable in this statement. Okay, because x is not specific, that's the reason. Okay, and number two, just because two random variables have the same expectations, it doesn't mean that the random variables are necessarily equal. Okay, when it comes to linear transformations, they are, but most of the time they're not. Is it clear? All right, so that's basically that. These are the two things. Very, very important applications, and I'm going to use it quite frequently. This is basically one of the most important statements there is in econometrics. So this is also a kind of bread and butter, and I'm going to also basically, use it in time series, because when it comes to time series, I'm going to make assumptions about the noise, and I'm going to basically make assumptions where conditional expectations of the noise are involved given certain set of predictors. So predictors are basically explanatory variables in general. Okay, so given basically observations of explanatory variables, I make the assumption that the conditional expectation of the noise is going to be 0 in general. Okay, so sometimes here and there. Anyway, but that's it. Now, regarding the law of total variance, which also involves conditional expectations, you have the following statement. This allows us to calculate unconditional variances of random variables. So that's what I'm going to do. Unconditional variance of a random variable is going to be a sum of what? The sum of the expectation of the conditional variance. Again, conditional variance was defined previously. This is the conditional expectation of the square minus the square of the conditional expectation. That's it. So that was the conditional variance. And you take the expectation of that. Since x is unspecific, guys, this is also going to be random. So even it sounds like you have a variance operator involved, just as the case for the conditional expectations. Conditional variance can be also random if the condition is not specific. You understand what I'm saying? So that can have also an expectation, and you take the expectation of that. Now this will not be the conditional variance, because you find that the unconditional variance is equal to the expectation of the conditional variance plus the variance of the conditional expectation. So that's that. Okay, so this is basically the law of total variance. This law is also referred to as the variance decomposition. That's going to be important when it comes to linear regressions, because you might remember that the total variance is going to be the variance of the explained parts plus the variance of the residual parts, and that's it. So this is, the first one is going to be called the explain variance also, and the second one is going to be called the residual variance. Okay, so but from the theoretical perspective, so just for you to know, and I'm going to connect the two. All right, so yeah, these are the two statements that are involved. Again, these are one of the most important statements there is regarding econometrics, both in theories and applications. One of them is the law of iterated expectations, and the other one is going to be the law of total variance, and I'm going to apply them here and there, so you're going to see them in this course. All right, that was it for today. Are there any questions related to this lecture as well as the assignment? Okay, so keep in mind, just to remind you, next week is the deadline. Next Friday is going to be the deadline for the first assignment. Yeah, I would be happy if you register for this class and join it. So yeah, no, you're not going to regret this as far as, you know, I mean, I would like to teach you something, so that's it. Anyways, all right, so I don't see any questions, so then, of course, and I would end this lecture today. That was it for today. Thanks. Take care.